This course is to provide an introduction to high-performance data analytics and visualization, applying the constant weather and climate domain. The course aims to be very practical, so to give you a feeling of what can be done from this tool. This course is organized by CMCC and by our colleagues from DCARZ, Niklas and Florian. This is a part of the activities of the ESiWACE2 project, the Center of Excellence in Simulation of Weather and Climate in Europe. As one of its goals is to provide specialized training to transfer the knowledge and enhance HPC capacity in the weather and climate domain. So as you know, the course is organized in 4 2-hour lessons. We already had the first 2 ones in the previous weeks. And for those who missed the previous session, these have been recorded and they will be uploaded later on YouTube. Today we're focusing on data analytics and workflows with Ophidia. Also take the opportunity to announce that unfortunately next session on visualization will be postponed of 1 week, so it will be on the 3rd of November. You will receive the info for the session as usual via email. So as for the other session, a couple of notes before we start. Please mute your mic and switch off your webcam. Remember that talks are going to be recorded, so if you don't want to be recorded, please leave your camera and microphone always off. If you have any question during the lecture, please then write them on the Google Doc at the link we provided in the email, and we'll read them during the session. And also we have set up the virtual machine with the info and the tools and softwares for the training and hands-on part. If you are more interested about this ESiWACE2 project, you can visit the web page. So I think now we can start with the first talk. So the presentation, as said, will provide an introduction to data analytics workflows and the implementation with the Ophidia framework. This is just the outline of this session. I'll start with the introduction about the issues and motivation for the use of workflow systems for data analytics in climate and weather domain. And I'll provide an introductory description of the workflow-oriented features in the Ophidia framework. Then I'll show you some real-world application implemented as workflows, in particular a case of a multimodal climate experiment. And after that, Fabrizio will provide a more practical walkthrough of the workflow feature with some demo and hands-on tutorials. So as already introduced last time, the size of data available in the field of climate and weather is becoming more and more larger. So there are several challenges that must be addressed to support large-scale analysis. In the previous session, we focused more on aspects concerning parallel analysis and reducing data movement. Today, we'll devote our attentions more on the implementation of complex analysis. This analysis can be, as said, very structured and complex and access multiple data sets. So handling this complexity is not trivial. End-to-end workflow solution can be of great benefit from this point of view. The typical approach, which is followed by scientists, although it's worth to mention that there's been a change in the last couple of years thanks to the increase in availability of data science open source solution. But let's say the typical approach was, in fact, to write their own code for analysis by using different libraries or command line tools. This type of analysis can require the execution of 10 and hundreds, and in some cases also thousands of analytics tasks. So in case of large-scale experiments, also more advanced programming skills are needed to properly handle the task concurrency or an effective execution of this analysis. And also, this could also require some writing a code which has to be optimized, and this could be quite time time consuming. In fact, when we consider this type of analysis, the data parallelism can be at multiple levels. For example, it can be at the level of the single operator. So, for example, if you want to run a data reduction in parallel on the same file, but it can also be at the level of the whole data analysis. So, for example, we could want to run multiple operators on different data at the same time. To design the workflow management system can relieve the user from the burden of handling the orchestration of the tasks. It can also provide some nice additional features which are very useful for big workflows, like an automatic application of optimization and also fault management, which is critical to increase the resiliency of these very big and lengthy workflows. As a second aspect, workflow can also contribute, at least in part, let's say, to two FAIR principles, as a workflow can be described with a self-contained document, which is portable. It can be then reused by different users, fostering in this way also the shareability of this analysis. As I already introduced last time, just give a quick recap of the Ophidia framework, which is an open source project developed by CMCC, aims at addressing scientific data challenges, in particular data-intensive analytics on multidimensional data, primarily in the field of climate change domain, by exploiting the datacube abstraction. So as said, this is a performance data analytics solution joining both aspects from HPC and big data, and it implements as which in a paradigm by providing a server-side approach for running parallel and in-memory analytics. And of course, which is more relevant to this task, it provides advanced mechanisms to run complex experiments and large processing workflows on data cubes. So this is one of the main points in the Ophidia framework. Basically, it provides a client side and then a server side. There are different tools that can be exploited on the client side, like the Ophidia library that we saw on the last session, on the first session, and also the Ophidia Terminal, which can be used to run single task, but also entire workflows, which are then submitted and handled by the Ophidia server on the server side, running this on the high performance computing infrastructure or on the cloud resources based on the type of infrastructure which is being used. So let's now move to the main topic of this session. I said Ophidia provides an advanced support for the management and execution of complex workflows, which can be composed of hundreds or even thousands of analytical operators. Maybe some of you might be wondering what is a workflow. I'm not sure how familiar you are with this concept, but to give a very simple definition, it can be considered as a set of steps which are carried out sequentially based on a defined order. Of course, the structure can be more complex than a simple pipeline. It could also be, for example, a tree or a graph. Like the picture which are shown in this slide are some examples of workflows which are executed in the Ophidia framework. You can see these are composed of by multiple circles, which basically are the tasks, whereas the lines represent the dependencies between the various tasks. The order of the dependencies is typically from the top to the bottom. In the Ophidia framework, workflows are written in JSON according to a particular representation. We use the JSON format, since it has a lower overhead with respect to other formats like XML, and also they don't provide any strict schema for the file structure, so it is quite flexible to define a specific schema. The Ophidia Workflow Manager is able to handle the direct acyclic graphs of tasks, which basically are directed graphs, which are graphs with directed edges, in which there's like an order in the connection among two nodes, and this type of graphs should also not have any direct cycles, so to avoid the sort of recurring connections. We can think at the nodes of the graphs as being our tasks that we want to execute, whereas the edge can be considered as the dependencies. So thanks to this structure, we can define very complex workflows by also reusing other existing workflows. So this is the Ophidia architecture, a high level of this architecture. We saw this already last time. The architecture is very modular, composed by various layers, and it provides a lot of different features to address scalability, as mentioned in the previous time. Today we'll mainly focus with this first layer, which is the Ophidia Server, the front end of the system. It exposes multiple interface for client-server interaction, and this allows also for an improved interoperability. So, for example, we can exploit a web service which is based on SOAP over HTTP, or also an OGC WPS compliant interface. The server, in fact, handles also the user authentication and authorization in order to support remote connection, but it also takes care of the management and scheduling and submission of both tasks and entire workflows. The task submission procedure has been implemented to be very flexible, and it can interact with different types of resource managers. We have tested it with LSF and SLARM, which are two of the most well-known type of resource manager. The Ophidia Server hosts the workflow management system, which support the orchestration of the workflows. The terminal and the PyOphidia module can be then used to interact with the server for the execution of Python apps or workflows. Here we can see a snapshot from the Ophidia Terminal, which is very similar to a Bash command line interface. It provides many of the features of a classic shell, such as auto completion, command history management, the opportunity to define environment variables, command analysis, and so on. But it also provides the features to run and monitor the workflows, as we will see later. Basically, what it does is translates the commands into the proper request and submits them to the server side. It can be very useful in different cases, for example, for fast and interactive testing, but also for doing sort of debugging of the commands. And I said, is instrumental for executing batch workflows. In this video, we can see a simple command, the OPH list that we saw on the first session, by using the key value format already introduced. And this is the example of the output. This is a more detailed view of the Ophidia server, in particular of its main component, which is this part here of the graph. Includes all the blocks that are used by the workflow management system. This part is very structured. The workflow management system takes care of parsing and validating the workflow, as well as substituting the parameters at runtime. It prepares the command to be executed and schedule their submission on the resource manager based on their dependencies, which are specified in the JSON document. Independent tasks can be executed concurrently by the workflow management system. Then it takes care of monitoring the job execution and keeps updated their status. And once the workflow is completed, it sends the response back to the client to inform of the completion of the workflow. The workflow management system takes also care of handling all the advanced rules and syntax which is defined into the JSON request. We will see this in a couple of slides. So as said, the definition of a request is based on workflow schema, which defines the rule for the implementation of the JSON representation. In the case of the Ophidia Server, we implemented a schema which is able to model direct acyclic graphs of tasks, and this is an example of this type of graph. It defines both the semantic and the syntactic rules which have to be followed by this JSON request. It introduces various abstractions such as global properties, which are shared by all the tasks into the workflow, and also flow the dependencies. It supports the execution of simple tasks and also of massive tasks, and then parallel groups of tasks which could be applied on different input data, as well as option to control the flow and also control the execution in case of errors, and provides also some interface for interleaving and interactive tasks which allow to stop or delay the workflow execution based on some input signals or external conditions, like for example the availability of a given file. Now we're going to see details in the next slide some of these interfaces, and later we also see how these are applied in practice during the demo and hands-on session. Here we can see JSON representation of the workflow, which is then translated into this graphical representation. So these circles are the actual task, whereas these hexagon-shaped blocks here represent, let's say, some specific interface. In this case, we have the start and the end of the OPH4, which is basically the definition of a loop. So as said, the schema defines several constructs that can be used to build and control the workflow execution. This slide is an extract of the Ophidia documentation. So besides the possibility to specify the dependencies and the abstraction for controlling the workflow in case of error, the workflow management system supports also other features such as loops of blocks of tasks that can be executed sequentially, but also the possibility to run parallel independent branches and conditional workflow branches by using an if-else structure. Also, variables can be defined at runtime, and as said, the workflow is able to handle interactivity and wait for an external condition to happen. Here we can see one of these interfaces, which is interesting to show. This is the interface which allows the interactive execution of the iterative execution of blocks of tasks. So basically, this models the abstraction of a for construct. So it allows to run a sequential iteration of tasks based on a certain condition, and this can be embedded into the workflow or provided at runtime as an argument of the workflow. The abstraction can be used to repeat the execution of a block of specific tasks over different input data or over the results of the previous iterations. So block of tasks are the blocks of tasks that have to be executed by each iteration are described between the OPH4 and N4 operators. The task within the iteration can still be executed concurrently according to their dependencies, and also this interface can be used in a nested fashion in order to run a sort of loop inside loop execution. Here you can see on the right side of this slide the picture that show the shape of the workflow at definition at runtime. So when the workflow is actually managed by the workflow management system, the colors in the picture will be explained in one of the next slides. So for the moment, this is not actually important. So the circles which are inside this rectangle box are basically the tasks which are assigned to a specific iteration of the loop. Additional information can also be found, of course, on the Ophidia documentation website. This previous interface can also be used in a different way. So as said, it can be used to apply a set of tasks sequentially and in an iterative fashion. But when we are applying this on multiple datasets, it might not be very efficient, because we might want to run the same block of operators on different data. So for this particular case, we provided an extension to the for interface to support parallel task execution. So in this way, the iteration of the loops are expanded by the workflow management system at runtime, as we can see here. And these are basically executed concurrently by the workflow manager. To do this, we simply have to specify this parallel equal yes argument, so that basically what we define when writing the JSON is simply this very simple structure that is defined by the begin and the end of the for and the task that we want to execute, and then we can expand this at runtime to apply it in parallel on different parts of data. So we can apply this, for example, on different data sets, but also to apply a different operation, at least in terms of, let's say, parameters on the same file. So here, for example, we are doing subsetting on a yearly data by doing a subset for each of the different months. So we can apply this in parallel and get and extract, for example, the subset for January, February, March, and so on concurrently. So we don't have to wait the other tasks to end to do this. And this can be written with a very simple and compact representation. We also provide support for the selection interface, which basically models the if-else constructs from programming languages. It allows defining multiple paths of tasks that can be selected dynamically when the workflow is executed. The condition for selecting the branch are basically Boolean expression, which can be specified in the workflow statically or provided as arguments that can be embedded at runtime. Moreover, this can also be set as runtime as output of other tasks. As we can see in the figures, we can define multiple branches that will be then evaluated at runtime, so that only one of these will be executed. And this can be done through the OPH if, OPH else, OPH else if, and if abstraction, which meaning is quite straightforward. And again, this can also be nested in order to have more structured paths inside the workflow. This can be very useful. For example, if you want to define a general workflow that then is applied in different ways based on a specific condition. So we don't need to write a different workflow, but we can maybe just select different blocks of tasks to be executed based on a condition, which is also specified at runtime. So thanks to the VIS interface and the feature provided by the workflow management system, this possibility to effectively implement many different types of analytics workflows. This slide shows some example of the runtime execution of real workflows which have been implemented with the Ophidia for different types of applications. And here you can see the various outputs which have been produced by this data analysis on, and these are produced with different tools, like for example, like Python-based modules like Basemap or Cartopy, or also by the Panoply, which is a viewer for NetCDF grid and HDF files. So the workflow manager system, as said, takes care of the execution of the task in the proper order, according to the definition of their dependencies, and also monitors their status. Workflows, as we saw in the previous slide, are represented graphically from the Ophidia Terminal by using these circles and arrows, and this is done by using the graphics library. This slide shows a very simple workflow which is composed by only three tasks and the various states that each task can be. The arrows, as said, represent the dependencies among the tasks. So in this case, before the execution of this last circle here can start, the first two have to be completed. So what can happen is that once we submit this for the execution, the first state in which they can be is the running state. So these circles are colored with this orange color, and whereas this third one is still in a state which cannot be submitted. So it is colored in gray. And what can happen then is that if the tasks are completed successfully, then they're colored in this green color, and the third task can now start, since the two one on which it depends are completed. Or otherwise, if one of the tasks fails for any reason, say this is then colored in red, and then the third task could be executed. For example, if we define the rules to handle this type of failure, or the workflow will just be, let's say, blocked and on this particular state. When all the tasks are completed, then they will all be colored in green. So this means that there's been a successful execution. Here we can see again the terminal, and in this case, this is a very simple example of a submission of a workflow, which is called timed loop with this JSON file, and the other values here are basically the arguments that we are specifying as input value. And once we submit this, then the terminal will send this job identifier, which is this very long string. In particular, what is important is this last number here, which is the workflow identifier, which can be used to monitor the progress of the workflow. So by running this view command on this number, we can see the status of this workflow. In particular, in this case, this is completed. Here we can see that 82 tasks of the total of 82 tasks have been completed. And in the third table here, we can see a more detailed view of the various tasks, and we can see that the name associated to each task, and then the status of this task. In this case, of course, they're all completed. And then by setting a particular option into the terminal, we can also see can also have a graphical representation of the workflow by using this structure as we saw in the previous slide, and we can see the state of the various jobs. Okay, in this case, this is not actually the picture associated to this state of execution, because it was completely finished. But this is just for explanation purposes. So here we can see that various tasks can be in different states, and this can also be explored sort of in interactive way. So we can set another option that allows us to check the progress of the workflows with a particular frequency. So we can have a sort of an updated view at every n seconds, and this is helpful to see how the workflow is progressing and which is the current state, and also if it's going according to what we thought it could be is actual speed. We also define a visual data analytics workflow modeling language to support the design of analytical workflows. This provides a higher level abstraction with respect to the JSON representation, since it doesn't focus on technical details of each task, but rather it provides a higher level view, which is helpful, for example, if you want to describe maybe this into a document that has to be, I don't know, shared with less technical audience. It provides different graphical symbols to define tasks, input types, ordered dependencies, nodes, and so on. And this also be extended. We see some example of real use cases that we have defined by using this particular language in the next slides. Okay, so now move to some real-world analytics use case implemented with the Ophidia workflow management system, and so we can see what can be actually achieved. So in this first example, we can see a workflow which has been implemented in the scope of the EClipse project some years ago. In this case, we implemented a single workflow for 3 indicators. So this also can be useful in order to maybe share different parts of the workflow and the data processing stages among different workflows. So basically, what we've computed here was the monthly average, the anomaly of the monthly average. In this case, was the difference between the monthly average and the long-term average, and then the climatological monthly average, which was average along the days of the same months. This was done on a data set from with T-Surface temperature from ESA. It consists of a file for each day. So basically, there were a total of 7,000 files for the period, for this 30 years period, and it was a total of about 350 gigabytes. So this makes it a sort of data intensive workflow, although the number of tasks is not very big in this case. There were about 90 tasks, more or less, which produced 14 files as output. We can see in the lower part of the slides, there's like this representation of the monthly anomaly, which is generated with Panoply. The second example is still from the EClipse project. This has been another set of indicators which has been computed with a single workflow. Again, we have 3 indicators which provides information about the the snow off and snow on, which are basically the indication of the first snowy day in a season, and whereas the snow off is the first day after the end of the snowy season, and then we have the number of days, which is the difference between the snow off, the snow on, and snow off, which represent the length of the snow season. And in this case, we use the ESA globe snow input dataset, which span this period of about around 30 years. And here we can see that in this case the workflow is much bigger. It comprises about 600 tasks, as we can see in the lower part of the slide. In this case, to implement this task, we didn't actually wrote this workflow with 600 tasks, but we used the OPH4 with a parallel extension in order to run the branches concurrently on the different files. And the picture on the right of the top right part of the slide shows an example of the output generated with the Panoply tool. This example is an implementation of a multimodal experiment data analytics. So in this case, this represents the precipitation trend analysis use cases, which has been implemented as an Ophidia workflow. The picture provides a graphical representation by using the modeling languages that was shown in a couple of slides before. I said this circle represents an Ophidia operator applied to a data cube, whereas the arrows represent the data flow, the dependencies. This workflow consists mainly on two stages. So in the first part, basically there are multiple identical sub-workflows which are computing the precipitation trend analysis over the data of the single model. And for each sub-workflow, you can see there are two identical pipelines which extract the precipitation trend from the historical and future scenario datasets. In this case, I think it was the RCP 8.5 from SMIP experiments, and this is done for each input model. This basically performs the import of the data, a temporal subsetting, and data reduction operation, and then it computes the trend through a linear regression operations. And these two branches are then compared and produce a set of netcdf file that are then and then this can be used in the second part of the workflow, which is the single model precipitation trend analysis. So after the precipitation trend analysis is being completed in the second stage, all the workflow are combined together to do this multimodal statistical analysis, and some values are computed over the trend from the various models. So this includes, for example, the average, the minimum, maximum, and the standard deviation. This experiment has been designed to scale with the number of models involved. We've tested this with different models from SMIP5. This table provides just the set of models that were used to test this in the one of the latest versions. In this case, this has been done on 18 models, and we'll see a video recording about the actual execution of this workflow in a few minutes. We have taken this different input data from the various models from the SMIP5 experiments, and the goal would be to port this also on SMIP6 data. So here we can see a snippet of the JSON implementation of the workflow. The full workflow is available on GitHub, in case I can also share the link if someone is interested. At runtime, this is translated into this graph, and we can see that the structure is basically reflects what we implemented in this high level representation. So here we have the various branches specified for the different models, and this second part here is then associated to the merging of this various trend analysis data, and this last part is concerning the multimodal data analysis. After this is completed, then the output is a set of maps, for example, which are produced based on the NetCDF files with different statistical analysis. This is done with CartoPy Python library. So now I'll just switch to the video. So just to show you how this actually works, it doesn't take a long time to run this on 18 models. So okay, I see that the video is being shared. So here we can see the execution of the precipitation trend analysis, and we can see that this is the JSON document which is associated to the workflow. Here we can see we have defined the various tasks with the arguments for each one, and then for this we also have the dependencies that are associated to each task. Here we define this loop interface by using this parallel, so it means that we are running in parallel this on the various models. And we can see the definition of the various tasks that are associated with the dependencies. And we can submit this to the terminal, but since we want to monitor the execution, we can set these variables here. This allows us to see this picture that is going to be shown here. We have submitted the workflow by specifying the name of the JSON file, which is optimized precipitation trend analysis, and the set of input arguments, which are, for example, the models and so on. So after the submission of this, the terminal will show this. Actually, in this case, we are showing just the static definition. This is how the workflow is basically a graphical representation of what we've written, because we've used this check command. So check can be is a command that can be used to check the structure of the workflow before we actually run it, and then we can run the workflow by just providing this command without the check keyword. So here then we will see that we'll have in a few seconds the graphical representation of the whole workflow. This is being executed on the Ophidia Lab system, which is a small cluster of fat nodes, which is deployed at CMCC. Here we have a total of 100 cores, and this is useful because in this case, since we are running on different models, this can allow us to make the execution faster. Also because we are doing this on multiple data. And on this left top part of the video, we can see this monitoring system, which is based on Grafana, which shows basically the core usage for the various nodes. We can see that the workflow is progressing. Here we have the different branches for the various input models. There's these green circles as those which have already been completed, while these light orange circles are those which are ready to be executed but are in a pending state, because the resource manager is basically full and it cannot, let's say, run other tasks until those that are currently running will be executed. So as they run, we can see that color changes from gray to orange, and then it becomes green. And as the tasks are completed, the dependent one can be submitted for the execution. In this case, the input size is of the variable models is quite heterogeneous. So as we can see, there are some branches which are being completed sooner, and others that can take slightly longer. And this basically depends on the import operator. In this case, we are doing this on 36 data sets and 2 experiments of data are from the historical and RCP 8.5 experiment. And the total data size of this is about 150 gigabytes. And among this, 25% of this data is being loaded for the analysis. So after the first part is completed, then the various single models are merged together, and the statistical analysis is performed in this last part of the slide. And so now we can check the execution. We see that 282 tasks have been executed. All of them are in complete state, and we can go and check the results of the execution on the thread server that we also deployed on the Ophidia lab infrastructure. That was an example of one of these outputs which is being produced, and here we can see another one which is the basically the maximum temperature. So I think I can switch back to the slides. And so this was just an example of an actual implementation of a workflow. So getting back to the slides, I would like just to show you an interesting point which links to one of the first slides of the presentation concerning the issues of in climate experiments. So we try to implement the same multimodal experiment also as a Python notebook by using the Ophidia API showed in the first session. And this is the what we can see on this left side of the slide. So although the first impression is that writing the code in Python might seem easier than writing the same thing using the JSON format, this is not that simple, because unless the user is quite proficient with some advanced Python programming, like for example multi-threading and multi-processing, this could be not very trivial. And in this part, we have the JSON file that we saw in the previous example. So in order to actually run the task in a concurrent way, we have to exploit this multi-processing mechanism, which allows to run the Ophidia tasks concurrently from the same notebook. But even while doing this is still slower than what we can achieve with the workflow manager for the Ophidia server by basically with the Ophidia server, this is 1.3 times faster. And besides this, while using the JSON format, we don't even need to take care of handling the concurrency of the task by implementing the specific code. So the workflow in this case can be quite helpful. Before concluding, I'll just give a quick summary of what we saw today. So in the first part of the talk, we started from the main issues concerning complex data analysis for climate change and how workflows can ease the implementation and support this type of analysis. Then we saw how the workflows are managed in the Ophidia framework and some of the main interfaces for controlling and also for controlling the workflow progress. The workflow management system has been effectively used for different real-world use cases where complex data analysis is required. In particular, I presented the case of the multimodal analysis. And this talk was aimed at providing some sort of an overview of the main concepts that will be explored more from a technical point of view in the practical part of this session. In this slide, I leave you with some readings related to arguments cited during the presentation, as well as further reading. And with this, I end this part of the presentation, and thank you for your attention. If you're interested in Ophidia, you can get additional info on the website. And also, please feel free to contact us if you want to get additional information about the framework. With no further delay, I'll now leave the floor to Fabrizio, which is going to present the more practical part. So, Fabrizio, the stage is now yours.
Thank you, Donatello. Hello, everybody. My name is Fabrizio Antonio. I'm a junior research associate at the Advanced Scientific Division of the Euro-Mediterranean Center on Climate Change. In this session, I'll show you the basic usage and some advanced features related to the Ophidia workflow. First of all, as indicated in the README file located on the desktop, we need to start the Ophidia Server, which represents the front end of the system. So from the shell, you run this command to start the Ophidia Server. The Ophidia Server manages the user authentication and authorization, and it is responsible for submitting the analytics operators through the analytic framework on the compute nodes infrastructure. On the other end, in this demo, we don't need to start the Ophidia in-memory I/O server. In the previous session, we introduced the concept of I/O server, which is responsible for parallel I/O with underlying storage system. And we saw that there are two types of I/O server used to store data: the in-memory I/O server and an implementation relying on the MySQL relational DBMS, which has been extended to support write-based data type and primitives. In this demo, to avoid memory issues related to the limited virtual machine resources, we will use the second one. Before starting, please check also that you have the latest version of the training materials. The repository for the materials for this third session is placed on the desktop under the HPDA VIS training, and the folder is named Session 3. To get updates, just run the git pull command into this folder, and this will check if there is any update on the GitHub repository. Once the environment has been started, we can run the Jupyter notebook under session 3. There is the outline notebook, which provides a summary of all the notebooks available in the folder. And as indicated in the preliminary info section, to run the demo notebooks, you need some SMIP5 data files, which can be downloaded from the ESGF repository using the provided links. Okay, now let's start with the first notebook, Workflow Overview, which is located under the demo folder. This notebook shows how to write and submit a request file for the workflow manager using the JSON format. We'll start with a very simple workflow, then we'll see how to build more structured workflows with Ophidia. First of all, import the PyOphidia module. I don't know if some of you have attended the first session where we introduced the PyOphidia. By the way, PyOphidia represents the programmatic interface for the Ophidia framework, and it is a convenient way to submit requests to the Ophidia server or to develop your own application using Python. Then we set up a connection using the setClient method. In this case, the connection parameters have been exported through the bashrc file. So we can set redeem to true, and the function will automatically retrieve the required information, the username, the password, the host, and the port. The following JSON object is an example of workflow with 3 tasks. One independent task named import, used to import an SDF file into a datacube, and 2 dependent tasks named subset and export to respectively perform a subsetting operation along the dimensions of the datacube and export the result into a new NetCDF file. And this is the simple task graph associated to the workflow. We will save all the output products in a specific folder named output, located under the data folder. So we have to create this folder if it doesn't exist yet. Okay, now let's start building the first workflow step by step. First of all, we define several global attributes, which include a number of metadata and default parameters values common to all the tasks. Some of these keywords are mandatory, such as the name, which is the title of the workflow, author, the author's name, and abstract, which is a short description of the workflow. The parameter exec mode specifies the execution mode, synchronous or asynchronous, and it refers to the entire workflow, not to a single task. In a case of synchronous mode, the workflow will be executed in a blocking way, so we will have to wait until it will be finished to display the results. Another important parameter is the number of cores per task, and cores, which specify the default value to be associated with all the workflow tasks. Of course, this value can be overridden with another one to define a different behavior for a specific task. By using onExit parameter, we can select the cubes that will be removed when the workflow ends. Here, we set onExit equal to OPH delete to remove the output cubes. Each task is identified within the workflow by its name, and it is related to a specific Ophidia operator set as operator. According to that operator, we can define a JSON array of key value pairs in order to call the operator with the proper arguments. The first task, named import, is related to the OPH import NC Ophidia operator. We are specifying several parameters, and in particular concerning the source path and the measure arguments. These 2 arguments, the values of these 2 arguments will be replaced with the first and the second workflow input parameters before sending the request to the Ophidia server. In addition, we can specify other arguments, such as import metadata equal to yes, to also import metadata from the input NetCDF file, impdim equal to time, to arrange data in order to operate on time series, and impcomset level equal to d, to set the comset level to day. The second task is related to the OPH subset Ophidia operator. In this case, we want to consider the whole spatial domain and specify a subset only on the time dimension, as indicated by the subset dims argument. There are several ways to specify a time filter. Here we are selecting a particular season, the summer season, by using the corresponding code JJA in the subset filter argument. An important aspect regards the dependency specification. In fact, the subset operator requires as input cube the output cube of the previous task, the import. So we have to specify a dependency between these 2 tasks. The dependencies can be specified by a JSON array put in the section dependencies of the dependent task. We can specify several items, each one related to a specific parent task, which the child depends on. In general, each item consists of the name of the parent task, the type of the dependency, In this case, we use the type single, since the child task exploits only one output of parent task, and the operator argument, whose value is depending on the output produced by another task. By default, the argument is set to cube. In a few words, this means that the cube argument of the subset operator will be equal to the persistent identifier of the datacube produced by the parent task. And finally, we can export the subsetted cube by using the OPH export and see-through operator. In this case, we have to provide the arguments for the Ophidia operator, so the output name and the output path, and set a single dependency from the previous task. Okay, now the JSON object for our first workflow is ready. We just have to define some variables that will be used as input arguments for the workflow execution, and in particular the path to the netsdf file to be imported, the netsdf file name, and the variable to be imported. To submit the workflow within the notebook, we can use the wsubmit pyophidia method, providing the workflow name and the input parameters. In our first example, the workflow has two parameters: the source path used in the OPH import and see operator to load the netsdf file, and the variable name used to set the measure argument of the import operator. The output of the workflow is a report with the final status of each task. By default, three objects are included: the workflow status, in this case, OPH status completed, the workflow progress, which reports the total number of tasks and the number of completed tasks, and a table, workflow task list, which reports a list with some information about each task. We can check the exported file, is named jja.nc. This file contains the task max values over the JJA period for the whole special domain. As we can see from the list method, the workspace is already empty, so we have no data cubes because we have used onExit equal to OPH delete as global attribute. We just need to remove the container automatically created by the import operator. By default, the container name is equal to the name of the imported file. Okay, now let's consider a slightly more complex workflow in which we are going to import and subset multiple netsdf files in parallel, merge all the subsetted data cubes, perform a reduction operation, and export the output data cube. As input files, we can use the daily netsdf files produced by the CMCC CM model and related to the task max variable for the years 2011 and 2015. In your version, you will work with files from 2011 to 2013, just to speed up the download process and reduce the number of files to be downloaded. In this workflow, in addition to the Ophidia data import, export, and analysis operators, we are going to exploit the OPH4 and OPH-N4 flow control operators to repeat the execution of one or more tasks, the import and the subset tasks in our case, over different input data. By default, the iterations are executing sequentially because data obtained in a cycle could be processed in next cycles. Since in our case, the iterations are independent from each other, they could be executed in parallel to reduce the workflow execution time. And this is the task graph associated to the second workflow. Again, let's build the workflow step by step. This is a whole JSON object associated to our workflow. So let's start step by step. In this cell, we define some global attributes as in the previous example. Then we create a new container to organize data cubes. We just have to provide the proper arguments to the OPH create container operator, in particular the container name, the name and the type of the dimension allowed, and the concept hierarchy name of the dimensions. The OPH4 operator is used to configure the iterative block and to set a number of loops to be executed. The values parameter is an ordered list of pipe-separated labels, the years in our example, to be assigned to the iterations in order to distinguish one cycle from another one. The key parameter is the name associated to the list values and is used in the inner task to access the current value of the label in each iteration. We set parallel to yes for parallel processing. In this way, the engine transforms the workflow into an equivalent version in which the iterative block is expanded into an independent sub-workflow. In our cases, 5 sub-workflow, and in your cases, 3 sub-workflow as the years to be imported. And finally, we define a simple flow dependency, since this task has to begin only after the previous create container task is finished. Now we define the two inner task, import and subset, which will be executed in parallel over multiple data cubes. The two inner tasks depend on the OPH4 task, so that we can exploit the value of the label associated with the current iteration. Regarding the import task, the main aspect here regards the source path parameter, which is defined in a parameterized way to get the current value of the year for each iteration and import the corresponding SDF file into the Ophidia framework. And this is the way to get the current value. In a similar way, the description parameter depends on the ER key to distinguish each imported data cube. The subset task has two dependencies, a flow dependencies from the start loop task to get the current value of the label, which is used in the description parameter, and a single dependency from the import task, since each subset operation has to be performed on the corresponding data cube imported at the previous import step. So the output from the import task is the input for this subset. To end the iterative block, we use the OPH and for operator, which has no arguments and depends on the last inner task, the subset task. In this case, the dependency type is set to all. In this way, it is able to gather the persistent identifiers of all the cubes generated by the subset task and transfer them to the next task. Okay, now the 5 subsetted data cubes, in your case the 3 subsetted data cubes, can be merged into a single data cube by using the OPH merge cubes operator. The resulting data cube will contain the JJA subset for all the imported years. Also in this case, we need to specify a dependency type equal to all in order to get all the data cubes persistent identifiers from the previous task. In addition, we have to set the argument parameter. By default is cube, but the OPH merge cubes operators requires a parameter named cubes, which will be set to a list of pipe-separated bits retrieved from the end loop task. Now, using the merged data cube, we can perform a reduction operation with respect to the implicit dimension, time. To do that, we define a single dependency between the reduced task related to the OPH reduced Ophidia operator and the previous merge task. Now we can export the output datacube to an SDF file by defining an export task that depends on the reduced task. And finally, we define a task to delete the container and empty the workspace. Now, let's submit the workflow. The execution mode is set to synchronous, so it will display the results when it is done. In the meanwhile, we can check the execution using the Ophidia Terminal, which provides the command view to inspect the output or the status of the workflow. We can run resume 5 to see the last 5 commands launched in the session, get the workflow identifier, and run view workflow ID 05, view the status until the workflow ends. And in this case, we have an update every 5 seconds. The green disk represents the completing task, while the orange disk represents the running task. So the import and the subset have finished. And now the whole workflow has finished. We can go back to the notebook, and we can check the exported file. In this third example, I'll show you how to exploit the selection interface to execute one or more tasks based on some Boolean condition that could be checked at runtime. In the following workflow, we'll consider a selection statement with 2 selection blocks, as shown in the task graph. And this is the JSON object associated to the workflow. So, as in the previous cases, we define some global attributes. Then we have to define the if and else blocks. What we want is to import data into the Ophidia platform from an external source, and we'll use the selection interface to code 2 possible implementations. In the first case, we want to import only the subset from the input file. In the second one, we want to import all the dataset and then extract a data subset. The actual implementation to be adopted is selected by means of an input parameter, as indicated in the arguments of the OPH-if operator. So a non-numerical non-zero value for the first option and 0 for the second option. The set of tasks belonging to the branch that begins from OPH-if and ends to OPH and if is the sub-workflow to be executed in case the condition set for OPH-if is satisfied. In our example, there is only one task related to the OPH import and see operator, and has a flow dependency from the if block task. To import only a subset from the input file, we have to specify subset dims, the dimension names used for the subsetting, subset type equal to core, so that the filter is considered on dimension values, and subset filter, which is a list of pipe-separated filters associated to each dimension specified in subset dims. And in this case, it's set according to the 4th workflow input argument. The task with the OPH else operator has to be a child of the task with the OPH if operator. It has no arguments. It simply starts the last subblock of a selection block if. Inside the else block, we define the sub-workflow to be executed in case the condition set for the OPH if is not satisfied. In our example, we have two tasks. The first one, import data, is related to the OPH import NC operator and is child of the task with the OPH else operator. And the second one, subset data, is related to the OPH subset operator and has a single dependency from the import data task, since the input datacube to be subsetted is the datacube generated from the import task. The last task refers to the OPH and if operator, which simply closes a selection block if. This task has two dependencies from import and subset, which is the last task inside the first sub-workflow, and from subset data, which is the last task inside the second sub-workflow. This allows gathering the identifier of the output datacube produced in each of the two branches. Here we define some input arguments, the path to the netsdf file, the netsdf file name, the variable to be imported, the subset filter for the latitude, longitude, and time dimensions, and important subset, which is a flag to be evaluated by the if-else statement. In this case, the flag is equal to 1. So if we submit the workflow and check the produced datacube using the list method, we can see only one datacube. So the datacube is imported, has been imported and subsetted at the same time. So we have only one datacube in our workspace. Now we can change the value of the flag, 0, submit again the workflow, and from the OPH list, we can see now two datacubes. In this case, the datacube has been first imported and then subsetted, resulting in two different datacubes. The second one and the third one. We can now inspect one of these datacubes. For example, the last one. And we can see that the size of the dimensions are according on what we choose in the subset filter input parameter. And as a last step, we empty our workspace. Okay, in the workflow overview notebook, we have seen a basic usage of the Ophidia workflow, how to exploit the iterative and parallel interfaces, as well how to use the selection interface to provide more flexibility by enabling the workflow manager to execute one or more tasks based on Boolean conditions. Now, I'll show you a real use case, the summer days workflow. So we'll see how to compute the summer days index as a workflow of Ophidia operators. As a first step, let's connect to the Ophidia server. Okay, this is the JSON object associated to the workflow. And this is the corresponding task graph associated to our workflow. So the first task is related to the OPH import and C operator used to import the NetsDF file specified by the source path parameter, which is set according to the first workflow input parameter, while the measure argument is set according to the second input parameter. Then we use the apply operator and the OPH predicate primitive to identify the summer days. In this way, we are creating a mask where all the data points which temperature greater than the given threshold are set to 1. This task has a single dependency from the import task, since it exploits only one output of the parent task. To count days above the given threshold on a yearly basis, we use the OPH reduce through operator with operation equal to sum and consent level equal to y. Also in this case, the task has a single dependency from the previous one, summer day mask. At this point, the reduce cube contains the summer day index for the whole spatial domain and for 5 years, from 2096 to 2100, the years which the input file refers to. We can extract, for example, the first year by using the OPH subset operator, and then export the corresponding datacube to an NetsDF file by using the OPH export and see through Ophidia operator. You can see both tasks have a single dependency from their own parent task. Subset depends on the count summer days task and export from the subset task. So here we define the workflow input parameter, path, file, and variable. You can submit the workflow and check for the exported file. Now, if we want to plot the summer days index for the exported year on a map, we just need to import the last datacube, which has a description equal to first year. So we can run the list method, identify the datacube. So in this string, we can replace the identifier and we can use matplotlib and cartopy to create a map. And finally, we can empty our workspace. We can go to the hands-on folder, and we can consider this notebook, Summer Days Workflow Hands-on. Okay, the workflow proposed in this hands-on notebook is basically a small extension of the Summer Days workflow that we run. In this case, instead of calculating the summer days index for a single input file, we want to compute the indicator for several input files in parallel by exploiting the iterative and parallel interfaces made available by the Ophidia workflow management system. So the inner tasks are basically the same than the previous workflow, but we need to add the for statement. So what we need to do is to use the pair of operators, OPH4 with the parallel option enabled, and OPH N4, put the import, mask, count, and export task inside the for statement, and adapt the dependency specification. So we can proceed step by step. Here again, the files that we are going to use for this workflow. And this is the JSON object. So we start with the first task, the create container. We use the OPH create container to create an empty container in order to organize all the datacubes imported and produced during the workflow execution. Then here we have to define a start loop task. So the import mask, count, and export task have to be now executed for each of the input years. So we use the OPH4 operator to configure the iterative block and in particular to set the number of loops to be executed. So in this start loop task, the values argument is an ordered list of 5 separated years to be assigned to cycles. The parallel option, as I said, is enabled. And each label value can be read in the inner task by using the year key, as indicated in from this argument. Each inner task depends on OPH4 in order to exploit the value of the label associated with the current iteration. The first inner task is the import, which is related to the OPH import and C operator, and the source path and the description argument are defined in a parameterized way to get the current value of the year key for each iteration. And as we can see, the task has a flow dependency from the OPH4 task. Then the second task is the second inner task is the summer day mask. Here, the OPH apply operator is used to identify the OPH apply jointly with the OPH predicate primitive. Is used to identify the summer days, so days where temperature is greater than a threshold. And this task has a flow dependency from the OPH4 task, start loop, and a single dependency from the import task. The count summer days task is used to count the days above the given threshold on yearly basis by using the OPH reduce operator. And here there is a flow dependency from the OPH4 task and a single dependency from the previous task. And at the same way, we define an export task. Each summer days index is exported to an SDF file by using the OPH export and see through operator. And here we have a flow dependency from the OPH4 task and a single dependency from the count summer days task. The iterative block ends by means the OPH and for operator. The end loop task has a flow dependency from the export task. And finally, we have a delete container task where we empty the workspace by deleting all the produced data cubes. So we can submit the workflow. And again, from the Ophidia Terminal, we can check the status of the workflow. running the view command on the new workflow. As we can see, each iteration is proceeding in an independent way from the others. The import and the apply are green, so have been finished. Also the reduce operator, and the whole workflow is now finished. So we can run the ls command, and as expected, we have an SDF file for each year that we have imported and processed. Now we can plot a map for each year and create, for example, a GIF image using all the maps generated. To do that, we have to install the image.io library, which is a Python library that provides an easy interface to create animated images, as well the NetSDF4 library, which is a Python interface to the NetSDF-C library. We can install them by using pip install and specifying the --user flag, which tells pip to install packages in some specific directories within your own directory without affecting the system Python installation. Okay, in my case, the requirements are already satisfied. We can run the script, and while the script is running, let's have a look to the code of the script. Okay. Here, basically, we are reading the previously exported NetSDF files by using the NetSDF4 library. And for each of them, we are creating a map using Cartopy and Matplotlib. Each map is added to an array. And finally, using the image.io library, we create the animated image starting from the single images. So we can go back to the notebook and check for the GIF image that we created. And we can also display this GIF image inside the notebook. And this is the GIF containing the 5 maps for the 5 years that we have processed. And that's all. Thank you for the attention. If you have any question, you can write on the Google Doc or on the chat. Thank you.
Okay, thank you, Fabrizio. Not sure if someone was able to actually run this in the VM. So if you try to do this and you have any issue, please let us know. Also, if you have any other question in general concerning the workflow management system, the idea was to provide you sort of an overview of what can be done with these workflows and how they can be applied in some real yet simple use cases, just to have sort of a feeling of what can be done. Of course, there are much more complex data analysis that can be implemented by using all the possible structures, including the or the if that was also shown by Fabrizio. Basically, opportunities to create workflows are quite wide. So the workflow management system is able to map very different types of data analysis. Okay, yes, so there's a question on the Google Doc. It says, I missed this part. Make sure the comment in the expo. I get, okay, yes, there should be an instruction at the beginning of one of the notebooks, like creating that folder, or otherwise you can simply add inside the notebook the Python commands to create the directory. Basically, by using a very simple command, is like os.makedir, and the command can be created. And the directory can be created. The Ophidia server, let's say from this point of view, doesn't manage the creation of the folders on the file system. So it assumes that these are already available, but there are also some commands that can be used, some Ophidia operators that can be used to manage the file system. So, for example, the OPHFS operator can also handle the creation of folders on the actual file system. In this case, it wasn't created; it was like expected to have it on the virtual machine. So that might be some point that was maybe. But anyways, these were just some simple examples. So with the workflows and with what's on GitHub, you can try to test this yourself. We also have very wide documentation. Maybe I can just give you a quick look about this, about all the possible things that can be done with the workflows. And so very complex workflows can be implemented. So I just can share the screen. So this is the Ophidia documentation website. So by using it, going in user guides, you will have the whole set of guides, and in the workflow usage sessions are some of the things that we discussed today. There are a lot of advanced features, the iterative and selection interface, and also the interactive interleaving, which was not discussed. It is more advanced and complex option, which allows basically to interleave the execution of the workflow with the task that can go in a sort of a waiting state. So they can wait, for example, for an external event. These are useful when, for example, if you want to implement sort of a operational chain where the workflow should wait for a sort of a file being available before going forward with the execution. And also there can be also some interactive tasks which can wait for the input from other workflows. So this allows different workflows to actually interact each other. So some information can be passed from one workflow to the other. And there are also some examples that you can, if you are more interested about this. Let's go back to the. So this was the second and last session concerning the Ophidia part. Also, it would be very helpful for us if you could give us some also general feedbacks about the organization of this session. So if you think if there is something that we can improve, so they can take notice about this. And I know that there have been some issues with the virtual machine, so that would be something that we'll be looking to address in the following training events like this. And okay, so I'll if there are any other questions, I think we can end the session. And by ending this, I just would like to remind you that the next session on visualization aspect has been postponed to the 3rd of November, so it won't be next week, or will be the following week. So just to be sure that this information is there. So thank you all for your attention, for participating to this session. Hope it has been helpful for some of you to have a sort of a taste of what you can do with these workflows. And okay, so see you online in 2 weeks then.